for giving me this opportunity to present my work this online platform. Myself is Dr. Sujeet Kumar Chaurasia, working as an assistant professor at the Center for Nanoscience and Technology, Professor Rajendra Singh Rajju Bhaiya Institute of Physical Sciences for Study and Research, Veer Bahadur Singh Purvanchal University, Jaunpur. Title of my presentation is the impact of in-situ formed silica nanospheres on physicochemical and ionic transport property of PEO-based polymer electrolytes. This is the outline of my talk. This talk is divided into the following section. First one is the introduction, in which I will give brief idea about the different types of the energy storage devices, and then I will discuss about their component, the electrode and electrolytes, and discuss about the different types of the solid state electrolytes materials, and then organic inorganic hybrid complexes, and then their method of preparation of these hybrid electrolytes, and some lab experimental results and discussion, and last one is the conclusion. Now in the introductory part I will discuss why we have to need a new functional material. As we know that in the 21st century the energy generation and its utilization probably one of the most important issue for the current scientific research worldwide. The electrochemical energy storage and conversion devices play a very vital role in various types of the energy storage technology. It can be used from battery to supercapacitor, electrochromic display devices, solar cell to the hybrid electric vehicles, and performance of these devices uh, basically depends upon the energy uh, basically depends upon the materials used in their power sources. Therefore, the performance of the electrochemical devices depends upon mainly dependent on the electrolyte material, because the transportation of the ions uh, takes place through these electroactive electrolytes material. So there is a need of new functional materials for our energy storage devices to meet the industrial and technological requirement, to meet the challenges related to health, sustainability and environmental protection, and to improve the quality of our life. One such class of electrolyte material is the organic inorganic hybrid electrolyte, which can be obtained by combining the organic polymer and inorganic filler particle at the molecular level by the sol gel method, which will be described later in later slides. On the basis of the given diagram shows that the Aragon plot for the various types of the energy electrochemical energy storage devices, which is basically the plots between the energy density and power density. Here we can see that the power density of the supercapacitor is higher than the rechargeable battery, but it has a low energy density. In order to enhance the performance of the electrochemical device, we have to simultaneous uh, increase the energy density along with the power without compromising the power density of the electrochemical devices. So, in electrochemical devices, as I have already told that the electrolyte is the main component. Because of it is the trade of the ions between the cathode and anode during the charging and discharging process, and so the which depend upon the performance of the electrochemical device basically depends upon its conductivity, ionic transport number, their electrochemical windows. So different methods have been used to enhance the uh, property of the polymer electrolytes, that is the copolymerization, plasticization, dispersion of ceramic filler particle like SiO2, TiO2, Al2O3, etc., and radiation of gamma ray to include the cross linking between the polymer chain. So one class of these electrolytes which have high thermal stability, high electrochemical window, high transference number, um, wider temperature range of operation is the organic inorganic hybrid electrolytes. Why we have to make the hybrid material? In the hybrid uh, material can be prepared due to the its create a material which specific combinations to properties by combining different molecular building blocks at the molecular level. Inorganic parts provide the high thermal stability, high mechanical strength, porosity, and which can be provide the mode channels, the path for the conduction process, and non-flammability. It also porosity. Inorganic parts provide flexibility, ease of fabrication, moldability, chemical stability. These are the factors which control the overall property of the hybrid material, that is the homogeneous distribution of the uh, filler particle in the in the polar polymer matrix at the molecular level, stable, no microphase separation occur. There is a specific interaction between the organic and inorganic part. uh, Structure property relationship, that is by changing the chain length and functional group, their property can be changed, enhanced. In in inclusion of the functionality, different functional group can be attached to these at the surface of the embedded filler particle uh, to provide a separate interface, and this that can be reduce the overall internal resistance of the between the electrode and electrolyte interface and trailing the molecular structure. So using these fact, using these type of the materials, we can synthesize the hybrid materials which structural from microstructure to nanostructure. These are the method of preparation of hybrid materials. There are two synthesis routes are adopted. First one are the building blocks and second one in situ. In building blocks, solution building, melt blending, powder blending, and sol-gel in situ method is the sol-gel assisted solution cast technique. This is the simple solution cast technique for the preparation of the hybrid electrolytes. First one, we prepared the organic component using the polar polymer PO, polyethylene oxide, with lithium trifluoromethane sulfonate, and inorganic part will be prepared by tetraethyl orthosilicate and glymo, uh, which is acted as a cross-linking agent between the organic and inorganic part. And this is the different weight. This is the following sample have been studied: OIE plus X weight percent Li. X represents the weight percent of the lithium salt added to the hybrid matrix. And this is the photograph of the our synthesized hybrid polymer electrolytes film with thickness about 200 to 300 micrometer. The X-ray diffraction pattern of these hybrid materials have been have been recorded, and we can see that the diffraction pattern of the pure PO is consisting of two intense peak at the 2 theta is equal to 19 and 23 degree, which is basically due to the crystalline phase present in the semi-crystalline PO when when the uh, it can be see that these peaks are riding over a broad hollow. Here we can see the broad hollow. Hollow is essentially the signature of the amorphous phase present in the polymer matrix. Upon incorporation of the different weight percent of the lithium salt to the pure polymer PO, we can see that the area of the hollow increasing with increasing the soil content, which shows that the hybrid electrolyte membrane having highest lithium salt content are more amorphous. We can also see that these peaks appearing in 19 degrees centigrade is shifted, slightly shifted in the hybrid electrolyte. This shifting may be possibly occur due to the partial structural modification in the uh, structure of the pure polymer matrix PEO. The thermal studies have been carried out using the DSC and TGA and analysis. Here we can see that the pure PO has the melting peak is approximately 65.8 degrees centigrade, which is shifted to lower temperature region due to after the incorporation of the different amount of the lithium salt, and this shows that the flexibility of the hybrid electrolyte membrane increases with increasing the salt concentration, and hence gives more conducting sample at higher salt loading. He- Using these DSC thermogram using the melting enthalpy corresponding to the melting peak Tm to the melting enthalpy of the 100% crystalline PO, the degree of crystallinity of the all the hybrid electrolyte membrane have been calculated. Here we can see that degree of crystallinity decreases with increasing the salt content in the hybrid matrix. This is the TGA thermogram of the our synthesized hybrid electrolyte membrane. The pure PO has thermal stability approximately 370 degrees centigrade, while the thermal stability of the hybrid electrolyte membrane containing different amount of lithium salt have more than 250 degrees, which is sufficient temperature range of the of the for their utilization in the electrochemical devices. In order to find out the possible interaction between the complexion of the polymer PO and lithium salt, as well as SiO2 matrix killer particles, the FTR spectroscopic study have been carried out, which can show that the formation of the SiOC and SiO2 group by enabling the vibrational band appearing at 1023 and 791 wave number. 1023 and 1791 wave number, as well as the complexation of the uh, uh, dopant lithium salt cation with the polar group of the PO, that is COC bond of PO matrix. This this slide shows that the Fe field emission scanning electron microscope of the our synthesized hybrid electrolyte membrane, which shows that the formation of the layered structure along with some crystalline domains, and which consisting of the silica nanospheres embedded within the layers of the polymer PO, and the layer has been formed due to a slow solvent evaporation from the surface of these hybrid matrix, which gives such a type of the layered structure which can be clearly seen here. This is the uh, TEM study of these our pure TEM micrograph of the pure SiO2 and hybrid electrolyte containing 5% of the lithium salt, which shows the well dispersed silica nanoparticles in PO polymer matrix having size approximately of the other order of 20 nanometer. The given slide shows that the temperature dependent ionic conductivity of the hybrid electrolyte membrane. Here we can see that on increasing the temperature, the conductivity of the hybrid membrane increases and follows the Arrhenius type activation process. And there are two regions. One is the below the melting temperature, and another is the after the melting temperature Tm, and the activation energy calculated for both the region. Here we can see that the activation energy decreases with increasing the salt content in the hybrid matrix, which shows that the easier transport at the higher loading, higher lithium salt loading samples, while the activation energy for the polymer electrolyte after the TM is slightly uh, changes, which shows that they can follow the nearly same type of the transport mechanism after TM. This is the electrochemical stability window of the our synthesized LS hybrid electrolyte. The LSV profile has been recorded between by choosing the stainless steel electrode and lithium foil. We can see that these hybrid electrolyte containing 28% of the lithium salt shows the electrochemical stability window of 5.2 volt, which is sufficient voltage range for the operation of uh, any electrochemical devices and utility. It's in solid state rechargeable battery, lithium ion battery and supercapacitor. The cationic transport number has been measured using the combined AC/DC technique using the following relation, and it can be found to be 0.39. At last conclusion, um, I will see that the in-situ formation of the inorganic silica SiO2 particle within the polymer matrix has been confirmed by the FTIR as well as SEM and TEM analysis. The formation of the silica nanospheres of size 50 to 20 nanometer disperse homogeneously in the layered structures of the po- polar polymer PO as confirmed by the same analysis. DSC results confirm the decrease in TM melting temperature as well as the degree of crystallinity with the lithium salt content, which shows that the higher loading of the salt gives the more flexible backbone, and hence we get higher value of the ionic conductivity. Ionic conductivity of the hybrid electrolyte increases with lithium salt content. It is found to be 4.6 into 10 power minus 6 Siemens per centimeter at room temperature and 2.1 into 10 power minus 4 Siemens per centimeter at 90 degrees centigrade for the 28% of the loading of the lithium triplet salt. The cationic transport number of the hybrid electrolyte for containing 20% of the lithium salt is found to 0.39. The above from the above discussion, we can see that uh, these synthesized organic inorganic hybrid electrolytes can be used as a separator membrane in the various electrochemical devices like lithium ion battery, supercapacitor, and solar cell, uh, etc. And so, thank you very much for your kind attention.